Hello and welcome to part 4 of the operating system series. Today I wanted to fix the bug that we had last time, so it's with the print macro. First we're going to put this here, and we're going to see that is already enough to get it to compile. So now we got it compiling. Today on the agenda is I want to start with multicore support. So what we're going to do is in our run.sh, we are going to specify SMP 4. That will give us 4 cores. And in QEMU, the cores are not started by default. So we need to write like a small driver. For that, we're gonna go ahead and say, let's see. For that, we're gonna go ahead and gonna say PSCI.rs. PSCI stands for PowerScape Coordination Interface, which is the standard interface on ARM on how to do stuff like turning on CPUs, turning off CPUs, turning off the system, and so on. And if we have a look at that real quick, 1 second, here. So if we have a look at this, there's a command that's called CPU on, and it takes as parameters a function ID, a target CPU, an entry point address, and a context ID. And these are passed in x0 to x3 in that order. So what we're gonna do is we're gonna first make a constant, say CPU on FID for function ID, and this is going to be a U32, and it is going to be the SMP64 version of the function ID. Then next what we're going to do is we're going to create a pub unsafe fn of CPU init, and it's going to take a CPU ID as U64 and a entry point as a function pointer. Okay. And next thing we gotta do is ASM. And in QEMU, the PSCI interface is hypervisor call is talked to with the hypervisor call of 0. And to that hypervisor call, we're going to do in out. In x0 will be CPU on FID, and the out part will be a return code. Okay, let return code, and that will be an I32 as far as I know. Why do I know that? Because in the specification it says return declaration is int32. It can be one of these, and they're defined in section 522, but we are not gonna worry about the actual value just yet. We're gonna get to that later. For now, we're just gonna implement everything and see if it works. So then in x1, we are going to have the target CPU. So it's gonna be CPU ID. CPU ID. In x2, we will have the entry point address, which is going to be our entry point. In x3, we are going to have a context ID. That is just a value that's going to be in x0 after it goes to EL1 non-secure code. So I'm just gonna fill it with the CPU ID for now. And what I'm gonna specify too is I am gonna specify what the options are. So options, and we're gonna specify no mem and no stack. And that is it. That should initialize the core for now. What we're gonna do for now is we're just gonna check the return code. Return code is not equal 0, and then we're just gonna print something for now. So kprint curl init CPU and this, and we're gonna say this is the return code. So CPU ID return code. Okay. Here we also gonna go and use core arch ASM, and that should be it for the PSCI. Then what we're gonna do in main, we are going to mod that thing, PSCI, and we're gonna do an unsafe of, let's see, also here we want to use create PSCI. We're just gonna use everything for now. And we're gonna call CPU init on, let's say CPU 1 for now. And to get the entry point, which is gonna be a start function, we're gonna do an extern C with a static and then or symbol. So that would be start, and it's gonna be a function. It's gonna complain about this, but that's fine for now. What we're gonna do then is we're gonna take the address of the start function, and that should be it. So it's gonna complain about this for now, but yes, double colon in PSCI. Okay, so what it's gonna complain about is it's not FFI safe, but we are just gonna tell it to not care about this for now, because we're not gonna use this for FFI anyway, so let's just say on this block of code we allow, oh god, no, improper C types. Okay, we got rid of that warning for only that variable. Now let's actually see what happens if we run this. It should not quite work, but okay. So what we need to do now is we need to check whether, so if we take this away for now, and we're gonna make it like very small, we're gonna say, actually, let's do it like this. For now, we're gonna do, we're gonna make a function that is gonna read the CPU ID for us. So what we're gonna do is in our start, boot.s, we are going to say, before we call into main, we are going to get in x7 the MPIDR EL1, which is the multiprocessor register. Then we're going to AND x7 with x7 and 0xFF, which is going to give us the core number. And then we're going to put the core number in TPIDR EL1, which is the software register. So we're going to use that to identify the core number in our program. So that would be x7. Okay. And then in main.rs, we are going to define a function. Call it CPU ID. and it's gonna return a U64 for now. Oops, what did I just do? U64, and let CPU ID is a U64 CPU ID, and we are gonna say unsafe ASM, and the same thing, MRS into a register. We are going to put TPIDR EL1, and then out reg CPU ID. Okay. And now we're gonna do ASM2. And let's try to compile this. It compiled. And then we're gonna say here, if CPU ID equal to 0, we are going to initialize everything. Okay. Or else we are just gonna print a hello message for now, so that we see that we bring up a new core. Hello from core something CPU ID. Okay, this still builds, and let's run it. Hello from core 1. Okay. Now, if you remember, we got 4 cores, so what we can do is 4 core ID in, let's do 1 to 4. We are going to use the core ID for it, and gonna run this. Okay, it only says hello from core 1 for now. It seems to get stuck. For core ID in. Okay, let's try to bring up core 2 and see what happens. It still says core 1. Okay, something is not going right here. So, Okay, are we getting the right core number in our boot S? We are ending it with 0x0. Okay, this should be fine. Is there a bug in our PSCI? We have a start address. We have the CPU ID. And this, and it doesn't print a okay. So UID is a U64. What if I push it, put it as a U size instead? That should probably be better. Let's make it a U size. Okay. Let's build and run. Okay, now we get core 3. That seems to be the bug. And now if we say core ID, okay, core ID. Okay, we get all of them. Sure, it looks garbled right now, and that is what we're gonna fix in the next episode, but for now, we have multicore. So the next is going to be an implementation for a mutex. But what I'm going to do right now is, since the episode is a little, let's say, shorter than usual, what we're going to fit in real quick is we are going to make a platform.rs file, and in that platform.rs we are going to use to define two macros that are gonna allow us to easily read registers and the system registers. So what we're gonna do is the same thing. We're gonna say macro export and macro rules. Let's call it read MSR. And then here we are going to take a register name, which is a literal, and that is going to be here. That is going to be a register value 64 of U64, and then we're going to do ASM. And to read the register, we are going to use MRS into register and then the register name. To get this together, we're gonna go do concat, and we are going to say reg name. That will concat the register name. Then we are in the out, we're gonna get reg value, and options are gonna be no stack, no mem. That is our macro for read MSR. So it's going to return the register value at the end. And then our second one is macro rules is write MSR. And for that one, we're going to do the same thing. So we're going to also say we have a reg name, which is a literal, but also a register value, which is an expression. Okay, so this is almost going to be the same thing. Here we want to get 2 more brackets. And now what we want to do is we want to do ASM, the same thing, concat. And what do we want to concatenate? We want to concatenate the MSR instruction with or reg name with a comma and the brackets. Okay. And then in here, the next thing we want would be, we want in a register the register value. Yes, in a register we want the register value. And that should be it. This should be the 2 macros that we need to read and write MSRs. So let's test them real quick. We are going to define another macro use. And we're gonna say mod platform And here, instead of doing all this, I'm gonna comment this out real quick. We're gonna say read MSR, and then we want read tpidr EL1. I think this should be it. And let's try to build this. Okay, in use of inline assembly, of course. This is still unsafe. Okay. We build this and it builds. And does it still work as we intend to? I am not sure, but we've got different cores here, so we'll figure out why the CPU ID thing is not working properly in a second or in the next episode, but for now, this is fine. We at least see that we have all cores, so let's try real quick. In run.sh, we are going to define our debug flags, and we're gonna say run. And then we are going to say rustgdb target remote 1 2 3 4 layout asm layout rex, and then we're gonna go here. I'm gonna break in the main function. Now what is it called? It's called main, right? Oh, whatever. Oh yeah, I didn't load the symbol. Add symbol file. My .os 0x. What was it? Or now I have to look this up real quick. It would be this one. We can automate this with a GDB file later on, but for now, yes, we're gonna load this, and now we can break on main. We can continue, and let's zoom into this for now. Okay, and let's see what happens. So we have CPU ID. It's gonna call an iterator. Branch into main, core range, iterator. Let's see. Switching to thread, yes. Okay, info threads. And all of the threads are running, so that means everything worked. Okay. So what did we do? Oh, and also due to the timing that we introduced, like with the debugger, we got all the output prints. But we're gonna fix them in the next episode with a mutex, a spin lock. And yeah. So what did we do in this episode? In this episode, we fixed our little mistake with the panic. We wrote a little macro for reading model-specific registers, or the special registers in ARM. Then we implemented the CPU init or CPU on function of PSCI, so that we can bring up QEMU cores, and we tested the QEMU cores with a little function that reads the core ID and prints it out to the terminal. And that is it for this episode. So if you have any questions, feel free to leave them in the comments, and I will see you in the next episode. At some point, I'm gonna also put the code online for you to view on GitHub. and then you can probably follow easier. So I will certainly set that up. All right. Thank you for watching and have a great day.